In this video, I'm going to introduce our work RLFTSim, realistic and controllable multi-agent traffic simulation via reinforcement learning fine-tuning. In autonomous driving, simulation models are used for training and testing of policy models prior to their deployment in real world. Here, behavior simulation plays a key role as in response to ego vehicle's action, it simulates the future actions for the rest of the agents in the traffic scene. For example, consider the left figure in which the blue car is controlled by the AD policy and the brown cars are controlled by the simulation model. In behavior simulation, we are predicting the microscopic actions for traffic agents given the map information and history trajectory of the agents. The future trajectory rollouts should be predicted autoaggressively as it is shown in the right figure. We studied two settings, goal-free generation and goal condition generation. The latter is what gives us controllability, and I will come back to it later. Prior work on traffic simulation falls into three buckets. Rule-based methods like IDM are light and easy to compute, but they only generate primitive behaviors. On the other hand, imitation learning methods give a strong realism and train efficiently, but they are open loop, meaning that error values compound at rollout time and no corrective behavior is trained. Reinforcement learning from scratch generalizes well, given a good reward. However, heuristic reward functions doesn't lead to a good realism. Meanwhile, human-like driving is hard to capture as a reward function. Our approach, RLFTSim, combines the best of all three approaches. We take an imitation learning based pre-trained model which already has a good realism and solve its alignment issues, for instance the error accumulation issue. We are fine-tuning it with RL using a comprehensive rule-based reward function via distribution matching. Here is how the framework is wired. We use SMART as the base model, which is an autoaggressive simulator that emits trajectories as half-second tokens. For an input scenario, we generate several rollouts, score each one via comparing it with the ground truth rollout, and update the policy with reinforced algorithm. Here we use a KL divergence regularization term to anchor the policy to the pre-trained reference model to keep the training stable. The realism metametric or RMM scores simulation rollouts across three feature categories, including interaction features, map-based features, and kinematic features. For each specific feature type, the values across multiple scenario rollouts and across time steps are gathered to form the simulated histogram distribution. Similarly, we get ground truth histogram distribution. RMM is measuring how much likelihood the simulated histogram places on the ground truth bins. These likelihood values finally are aggregated via geometric averaging over agents and time steps and linear weighted averaging over feature dimensions. Higher values for RMM means the simulation is closer to a real driving scenario. We should note that there is a problem with using RMM directly as a reward function. RMM is a set-based metric. It takes k equal 32 rollouts and returns a scalar value. That makes it sparse and sample inefficient. Our solution to this problem is metametric leave one out or MLOO reward formulation. Considering that a set of k rollouts, for each rollout I, we exclude that rollout from the set and compute the RMM on rest of the k minus rollouts. We assign that rollout a reward equal to the mean of the all leave one out RMM values minus its own leave one out RMM. This is shown in Formula 2. Intuitively, if removing rollout I made the group score go up, rollout I was dragging realism down, so it gets a negative reward value, and vice versa. The resulting MLOO formulation is a dense and low variance per rollout reward signal without extra sampling need. Here we analyze the variance scaling properties for RMM and MLOO theoretically. First, in proposition 1, we show that considering reinforced algorithm, the gradient estimate with MLOO-based reward is an unbiased estimator of the policy gradients for an equivalent RMM-based reward function with a smaller number of rollouts by 1. Then in proposition 2, we show that the variance of RMM scales inversely with the number of rollouts and time steps. Last but not least, in proposition 3, we showcase the superior variance scaling of MLU compared with RLU. Here, RLU is a similar baseline method, and it stands for reinforced leave one out, and it has similar density as MLU. However, this doesn't come with a favorable variance scaling, as we theoretically show and empirically validate as shown in the right figure. In RLFTSim, we also address controllability distillation via post-training. To do so, we explore two goal observation methods: vector extension via concatenation and goal indication via map to agent cross attention. These are specific to smart models architecture. Because reaching goal is rare during reinforcement learning exploration, we use hindsight experience replay to pair trajectories with previous terminal states. We then apply importance sampling to support these off-policy samples during policy gradient update steps. On the Waymo OpenSim Agents challenge, RLFTSim achieves state-of-the-art on the overall realism metametric and on the interactive submetric. Crucially, we outperform our own Smart Tiny reference model and a Smart Tiny CAT-K, which is a corrective sampling-based supervised post-training baseline on top of a Smart Tiny model. The results confirm that closed-loop RL with MLU improves realism beyond what imitation learning alone can reach. Furthermore, we evaluate the reward choices as its results shown in Table 2. Imitation-based mean AD and heuristic collision off-road rewards, either with or without additional AD term, barely move realism. RLU gets some RMM improvement, but MLU wins across the board with higher overall RMM, kinematic, and interactive scores showing its superiority. Here we show some qualitative samples. For the pre-trained model, on the left figure, the parked vehicle attempts to enter the road, which leads to a collision with the passing vehicle. The passing vehicle tries to slow down, but it cannot avoid the collision. For the post-trained model on the right side, the parked vehicle waits for the road to get free and then slowly enters the road. There is another collision example where for the pre-trained model on the left side, the vehicle entering the circle fails to yield to the pedestrian and collides with it. In the RLFTSim model on the right side, the vehicle yields to the pedestrian. For goal condition simulation, here we are showing some scenarios with two different goals. The goals are shown in magenta color. On the left side, the goal is a U-turn. This aligns with the ground truth behavior. Both the pre-trained smart and our fine-tuned model attains this goal. On the right side, we override the goal to a left turn. The pre-trained model cannot attain the goal, so it still tries to do a U-turn and it misses. However, RLFTSim with goal conditioning fine-tuning produces a clean, realistic left turn that reaches the target. Finally, in summary, we argue that imitation learning alone is not enough for traffic simulation and it needs closed-loop training. Our MLU reward formulation turns Waymo's sparse realism metametric into a dense, low variance per rollout reward. This makes RL fine-tuning sample efficient and leads to state-of-the-art realism on WOSAC challenge. By adding goal conditioning with hindsight experience replay, the same framework distills controllability, letting us steer agents to specific goals without hurting realism. Going forward, we are looking at limitations with RMM realism measurements, such as its saturation, and studying potential reward hacking issues by using RMM as an optimization objective. Thank you for your attention. We are happy to answer your questions either in the virtual forum or via email. Please check our project page and visit us at the poster session number 6 on Sunday, where my colleague Hunter will be presenting this work.